another CAM colloquium.
That's
so
right, yeah.
Georg Stadler is, he was at UT Austin. I didn't know him then. I met him after he'd come to Cornell, which was after I left Cornell. So he's been a professor there for some years now. We really got to know each other because we've been part of the science collaboration together. But he does a variety of things with numerical PDEs and some optimization and some uncertainty quantification and all flavor of numerical methods types of things. Today talking about going back to basics and talking about Newton method with some applications. With that, I'll hand it off to you.
Thank you. Thanks, everybody, for coming by. I assume this is loud enough, right? Yeah. Okay. Okay. So, yeah. So what I'm going to start with something very basic, something all of you probably know, and then I'm going to apply it to a specific equation, and I want to point out that this applies not only to this specific problem, but to actually quite a few problems. And then I'm going to show you a use of this kind of equation to do something that's a large-scale scientific computing project. So it's trying to start with basic and try to hopefully end up in something quite applied and quite challenging, at least from a computational perspective. So yeah, so I should say that Johann is an Argonne. He's a former student from my times in Austin, and he's going to actually move to Virginia Tech in next year. And Melody is a graduate student. She's defending in 3 weeks, fortunately, and they both have very important. And it's also something I like because somehow these things, these methods, these tricks, I've been using them on and off over several years, and I only recently realized that actually there is it's always a very similar trick. So the way I'm going to present it is actually not in the order that I've kind of used these methods. Now it looks kind of simpler, but I've kind of used it first in complicated problem, and now later realizing that actually there's some common structure to these things. So I'm starting very basic. I want to talk about Newton's method, which all of you know. So we have a nonlinear function from two spaces, can be finite dimensional, could be infinite dimensional or vector spaces, and I want to find the root of this equation. Okay, so that's it, f(x) equals 0. And then you'll know how to do this. Newton's method says, okay, so one way to do it is we linearize the equation, and that's f prime. If f is Rn to Rn, f prime is the Jacobian, it's a matrix, size n cross n. We solve f prime, or the Jacobian, times an increment, which I'm going to always denote by tilde functions, so that's a vector here, is equal to minus the residual, like the fxk. That's how I compute my residual. It means solving a linear system each time. And then I use the update step. My new step is going to be the old one plus the increment, the Newton increment. And yeah, that's Newton's method. Okay. Newton's method can be used to solve a nonlinear equation, right? But it can also be used to minimize an objective function. Okay. And what's the connection there? Obviously, and you also know that, right? If you know that to minimize a function, you have the first order necessary conditions, which means that the minimum, the gradient necessarily has to be 0. The gradient equal to 0 is a nonlinear function that exactly looks like this. The Newton's method of a nonlinear equation is kind of the same as Newton, more or less, the same as Newton's method to solve the first order stationary conditions for an optimization problem. Connections. If you have this structure that comes from an optimization problem, you know a little bit more. For instance, you know that the second derivative matrix / operator, this thing, needs to be symmetric when it comes from the second derivative of an optimization problem. So this object here needs to be symmetric if it comes from a second derivative of an optimization problem. In general, it doesn't have to. So that's a little bit you know a little more of the structure. You know. So basic stuff. What else do we know? I drew this morning on my iPad because I wasn't sure if I would have a board here, but I do have a board here, so that's why it doesn't look so amazing. What do we know? What can we say theoretically about Newton's convergence? Right? We know that shortly, Newton method converges quadratically, so very fast, okay, in a ball of a certain radius. We proved this of rho radius around the solution x star. So this might be a very small ball, okay, but you have guarantees that given certain regularity assumptions, right? In finite, you can have a version of this in finite and infinite dimensions. There is a neighborhood around the solution at which Newton's method is perfect. You can make full-length steps, you get super fast convergence, everything is good. Okay? Unfortunately, these balls can become quite small. So there are famous examples where you can show when you solve, I think, a stationary Stokes equations. The radius of that ball of nice Newton convergence decreases at a certain square root, a certain root order, I'm not sure, with the Reynolds number. So the higher the Reynolds number, the smaller the ball gets, and it becomes very, very small eventually. So it becomes quite tricky to rely on this convergence result. Because, because the radius depends to some level of nonlinearity from a function f. Okay, so that's something I can really control. Outside of those convergence regions, which typically is pretty much everywhere from my problems, you don't know, you're on your own, right? You can apply this, not so clear how to guarantee that you actually get into this region, unfortunately. There are certain tricks and methods, prove certain things on this, that you can use. You cannot make a full step, right? So you start outside somewhere here, you're far away possibly, right? So you get a Newton direction, x tilde, and you might not want to take a full step, but you might be more conservative, take smaller steps, and this is called damping, and that helps you often to get closer to that convergence regions. Okay? There's some other tricks, but that's kind of the problem. Finding a good starting point, somewhat nearby, right, is very, very hard, right? It's not so easy. So the question is now, for certain problems, can I maybe change my nonlinear problem f of x in such a way that this region where I can rely on this theorem becomes larger? Okay? Maybe I can make my problem somewhat nicer. And that's roughly what I'm trying to do, okay, on an abstract level. And let's try to do a few things. So how about the following thing? So let's think in finite dimensions, f of x equal to 0, n equations, n in my case might be very large, so thousands, tens of thousands, complicated system. How about we take any kind of matrix G, and we say instead of solving f of x equal to 0, I kind of have a random linear combination, a complicated linear combination of f of x, right? That's what this G does. And I solve this instead. I give this a new name, right? I call this h of x is equal to 0. Maybe that's easier to solve, right? Because I've multiplied it with this matrix, so I completely have a different linear combination of rows and columns, with list of rows. Maybe that's easier, okay? That would be nice. Easier in the sense that this convergence region is larger, right? This row is larger. And this is, for any invertible matrix or the operator, you could ask this. But it turns out that's not working, because Newton method has this property that's called affine invariance. That means if you have an affine transformation of your equation, affine meaning a linear transformation, the Newton update actually remains invariant, it doesn't change. And you see it directly from this equation, right? If you have a G, then the Jacobian has this G outside, and the right hand side also has the G. It's invertible, so you can just skip it, and the x tilde is going to be unchanged. That's called affine invariance. So you're not going to get anything new by doing this trick. But if you have an operator, let's say matrix G, right, that is not constant, then you might get something new, right? So if you multiply this with a G that's a function x itself, right, and then write down Newton's step, you get an extra term, right? You get this extra term here. And so you get actually a new, different Newton method. I'm not saying might, because you have now, when you solve for x tilde, this is the same as here, right? But the left-hand side is different. That doesn't mean that it's better, right? It might be very well worse, but at least that's a way that you can change it. Right? And on some level, that's the basic idea behind pretty much everything I'm going to show you. I will show it to you for complicated nonlinear PDE systems, but it took me a while to realize this. All these tricks I do to make them work, to make the Newton's method for this system converge, in some sense it's just this. I change it in a way that is not affine invariant, right? And by that I make it easier to solve. I'm not sure, by the way, if anybody has questions, please just ask. Right? So that's the high level thing. Any questions so far? Okay, so then this approach, I will target the following. I'll target a strongly nonlinear PDE of differential equation that models some fluid dynamics. the idea is not specific to this equation. It applies to more general equations. And actually recently kind of applied it to 2 or 3 other complicated systems as well. But it's not what I don't think it's going to be necessarily useful for any kind of equation, but for a class of problems this might actually be useful. This kind of trick that I want to pre-multiply it with something that is not constant, and that's why I actually get a new Newton direction. I can only do it for these systems if I first increase the dimension. I introduce a new variable. Okay. Then with this new variable, I can do a modification. I can do this nonlinear transformation. I can then write down my Newton linearization. And actually, I don't want to solve a system with more unknowns, so I do this on paper, and then I actually eliminate this additional unknown. Okay. So basically, the system size I'm solving is not larger. It's just different. So I go to a higher dimensional space, do my linearization there, and then go back into lower dimensional space. And I kind of knew this, but I recently realized that that's pretty much exactly what's being done in linear programming to some extent. Okay, so I'm going to show you this example now. They do a very similar trick. Okay. What is linear programming? Linear programming is solving a linear program. Okay. That's a very, very, very deep statement. Linear programs look like this. Okay. So you minimize a linear function over x. There might be equality constraints, x is to b, right? And then you typically have inequality constraints. All variables need to be positive. Okay. And the standard approach to solve these things is simplex method, which I might know. But the standard approach is shown to be more efficient is actually what's called an interior point method. Okay? And this is the first step to the interior point method. So what do? The main difficulty here, everything is kind of linear, right? The main difficulty here is inequality constraint. Every component of x, so when I write x equal to 0, x is a long vector, right? Every component needs to be non-negative. So one way to enforce this is to kind of just use a barrier method. So I'm going to remove this, but I'm going to add a barium term to that objective that pushes those x's that get too close to x is equal to 0 away from x is equal to 0. It prevents them from getting negative to enforce this. So it's a log barrier, standard thing. So this blows up when x goes to 0, and then this new weight just controls the strength of this log barrier. So you replace this, right? With the barrier method, and then it becomes a nonlinear program, right? Because this is nonlinear in x. So you can write down the first order necessary condition. It's convex, by the way, and you have to solve this nonlinear system of equations. Turns out, if you do this, if mu is very small, which means this still blows up, but it's very local to some extent, this becomes tricky to solve. This is now a nonlinear equation system. It's tricky to solve these things. Okay, so what do the interior point people do instead? What they've been doing, as I said, I kind of knew this, but how close it is to what I'm doing actually I realized more recently. So what they do instead is they take these two equations, the same ones as here, and they just introduce an extra variable. Go ahead and mention it. And this extra variable is for this one. So by the way, this notation u is a constant. It's just a number, the small u here. This just means component-wise division. So u divided by x1, x2. So all these are vectors. So that's all this means. Right? So the whole trick they do is now you introduce a new variable for this thing. U constant divided over this vector x. So we call it s. I think it comes from slack variable. You just introduce that. And you add this relationship, right? You replace these bets, you add this extra equation. So far, I've not done anything deep, right? Just nothing, all of the system. But now what I'm going to do is, what they do, we're going to do the same thing on a different level. Now I'm going to, so s is a vector, right? Mu divided component-wise by x. And now we're going to, the x's all need to be positive because they, in this approach, it can never become 0 or negative. Because this log blows up at 0. So they're all positive. So I can multiply each component, right, onto the other side. So I can replace this by here. Right, and I multiply to the other side. And that's still equivalent. That's an equivalent equation. Okay. This is the point, right, which I'm trying to point out. This transformation is not a sign transformation because I've multiplied with a g of x, right, in my previous notation. It's not constant, right, because the x is part of my variables. So here there's something happening that's going to give me a different step. So this is where the kind of thing happens. And then they call it perturbed Plasticity condition. So you now have to solve the system in 3 variables, s, lambda, these are vectors, and x. Okay. But the claim is, or we'll find out that this is actually nicer. This problem has a larger ball of Newton convergence potential. So what does it mean? So with the standard approach, there's a linear system that's going to look like this. With this new approach, it's going to look like this. But then we don't want to solve a system in more unknowns. It's more expensive in general. So we kind of eliminate, with paper and pencil, the new unknown we introduced, the S tilde, by just using a Schur complement, linear algebra. Because you have an equation here that says diagonal of S times x tilde plus diagonal of x times S tilde is equal to something. And that allows us to eliminate, to express the S tilde as part of the other variable, so we can take it out again. We come up with this system. That's only now the increments for x tilde and lambda tilde. So it's the same size as the original one, but it's different. And then after I solve this, I need to just update, compute my S tilde by, this is like what's called the Schur complement linear algebra. Yeah, so basically that's the trick here. And it turns out in this context of linear programming, it makes a big difference. In linear programming, they, besides this, which is called primal-dual approach, they also have this mu, which is in front of this log barrier function. They also want to drive this to 0. And they have ways to do this together as well. Yeah. So, okay, so that's this. And there's another example which is not linear programming. You can do actually, not optimization, actually, you can do a similar trick. So this is a 1D nonlinear partial differential equation. So it's just u double prime plus some constant, e to the u, so that makes it nonlinear, right? And it's a boundary value problem. So it's 1D, and they tell you, the values on the left and the right. And you want to solve this. Again, it's a nonlinear boundary value problem. You can play a similar trick here. So you can again introduce a new variable called v for the x of u. So this is the equation here. V is x of u. And then you instead of linearizing this system, you linearize this system. And this is what I do here. And then I come up with a Newton step that looks like this. So here I linearize this new system, and then I again eliminate the v tilde. So it feels like a little bit of a cheating, right? I introduce a variable, linearize, and then eliminate again. Make a difference here. It turns out here, this is exactly what you would get if you just linearize this directly. So here I've just introduced the variable, linearized, and then removed the variable again, so I don't get anything new. Because I didn't do this trick where I multiplied with a g of x that is in this, before doing the Newton step. So here I'm doing the same thing, but now for this variable, I transform it by applying a logarithm approach here. So I get this equation. Okay. Now I linearize this equation, eliminate the new variable again, and then I get a modified Newton step. Okay, so now I get this Newton step that is not the one I would have gotten before. So it's very similar to this, what you do in linear programming. Yeah, it's not clear that this is better to solve than the original one, but it will turn out it will. Why intuitively? Why is it better? Because somehow you've decreased the level of nonlinearity in your function. So Newton's method is a larger circle, and that's what makes the difference. Okay, so this is just a summary for this what's called Bratu problem. This is this 1D simple problem. Okay. For this problem, actually, these two approaches both work reasonably well, so you don't gain much by doing this for this problem. Okay. Let me talk about the real problem now. So this was all kind of like the fairly simple stuff, right? Very simple Newton, and linearization, and nothing kind of groundbreaking here, I guess. So let's look at the real problem. And this is not a problem I tried to find to play these tricks. So this was not like the problem where I have a tool and I'm trying to find a problem to apply it to. This was actually a problem that I knew beforehand. It was a huge grant a long time ago. And then it turned out it has this structure where these things actually make a huge difference. So it wasn't trying to find a problem to apply my trick to. So this is what's called visco-plastic Stokes flow. So this is, I'm going to show you the equation on the next slide. What this is, it's an integration of viscous fluid dynamics. So viscous fluid dynamics is the kind of fluid dynamics which is very, very low Reynolds number. Everything is very honey-like. Everything, there's no turbulence. Everything moves like a Stokesian. Very viscous. Yes, that's viscous fluid dynamics. And visco-plastic means it's quite nonlinear, and it can switch between two behaviors. Very viscous, very honey-like, and become very thin at some point. And so this is from a simulation I'll show you later. What you'll see is, what can happen is, so this is a simulation where we take this 3D box of very viscous fluid, okay, and we compress it from both sides. And then you get this localization, these areas where you get extremely high shear rates, very high stresses, and something happens, and the fluid kind of switches its behavior from very viscous here to very thin here, very kind of easy to change in these regions. And that happens not because I've predefined these regions, it happens kind of dynamically because that's what the fluid wants to do. It's a non-Newtonian fluid. And where does this show up? It shows up on many different scales, for instance, in anything related to earth science. So this is patches from a geology book where these things show up. And I have a video, I hope if the link works, where you see this kind of thing. This video actually is not exactly the same thing because it's granular medium, but it illustrates that effect. I'm not claiming that the same rheology I'm going to show you in equations then. Okay, so we need to get it around or something. So this is a video of an experiment where people put layers of sand into a box and then compress the box in a very similar fashion. It's a little bit different to some extent because sand is a granular medium, but the effect is actually very similar. So this is what you see. Okay. So okay, so it's a box, okay, and then they push the left wall of this box. These are different layers of colored sand. So it's just sand, and they push it, right? And what starts happening here, because they started pushing it, is in a certain angle you get this shear band. So basically you have initially it deforms like viscously, and then it localizes, and it gets these shear bands. And it switches from a viscous to a plastic behavior. Changes its kind of behavior. Okay, and it does this several times. It looks like this. So you see they push it, and then it generates this kind of shear band. So that's in the kind of visco-plastic fluid. I'll show you something very similar happens. Okay, so here it's sand. It's granular medium. It's not 100% the same thing, but and you can imagine from an equation that's the same equation that's describing both phenomena, like nice viscous smooth deformation here, and then generating the shear bands. Okay, then you see my history of YouTube videos I used to watch, I guess. It's always not too embarrassing. It's always the problem, yeah. Okay, great. So that's what you can think of. Okay. Why you see this? You really see this? We see this on different scales in geoscience. But by the way, this is not only restricted to geoscience. Similar phenomena happen in other areas as well. But this is a scale that is obviously like a rock kind of scale of some blocks in Utah. And if you look at them, right, you see very similar things. You see these kind of bands of where the rock is displaced, is obviously has been sheared against each other. How is rock a fluid? Rock is a fluid if you take rock on high pressure and extremely large time scales, you can model rock as a fluid. Over millions of years, rock flows very tinily. You don't see it, but that's what it basically does. So it happens on these scales, and you can see it everywhere. If you keep an eye on it, you see these things everywhere. And even on a larger scale, so that's from some simulations I'm going to show you, this phenomenon happens. So this is a much larger scale now. So here we're talking, I don't know, like a couple of 100 meters, right? Here we're talking even more into the Earth. That's the Earth kind of curvature here. So this is at the order of 1,000 kilometers roughly. And what kind of you see here, or what I'm trying to kind of show you here is, because that's later what I'm going to show you on the real problem is, it's what's called plate tectonics. Okay? So what's happening here is there's one plate that for some reason moves here to the left, and it's getting pushed underneath another plate. Okay? So plate tectonics is important because it's the reason for earthquakes, for tsunamis, for all this kind of stuff, right? And what happens when one plate kind of is being subducted under another one is it's only possible because the way plates, which is rock, right? Over long time scales, you can look at it as a viscous fluid. Over long, the reason why this is even possible that it bends here and subducts underneath another plate is because of that kind of nonlinearity I'm going to show you that allows the plate. It can bend here because of this plastic behavior. If you don't have this plastic behavior in your model, you will not get any of this. And if we wouldn't have this, we wouldn't have plate tectonics on Earth. We wouldn't have earthquakes, we wouldn't have any of this kind of stuff, right? So it's something very specifically that our Earth does. I'm not sure if any other planet does something similar to plate tectonics. Yes?
Is phase transformation important? Because you're heating up and it's getting friction, and so then there's going to be melting.
On that scale, I don't think it is. I don't think it is on that scale. So on these scales, I'll show you some large-scale simulations. Then I think that's not the word. The uncertainty is we have bigger problems than that. Let's say it like this. Anyways, but the reason why this plate can actually bend is because it behaves. It has this. It switches from viscous behavior here to plastic behavior here. That's why we played it. Okay, just to. Enough of advertisement, so now the equation, okay? So in some simple case, right, these visco-plasticity equations are just look like this. So that's a nonlinear Stokes equation, okay? You might have seen this in class. U is the velocity, so it's flow. P is the pressure. U is free. U has three components. P is a scalar component is the pressure. And the whole interesting part happens in this term here. This is where you describe the constitutive relation of the fluid. And this is a visco-plastic fluid. So this is given by either one of these, so we can do both. But basically, these laws here, they connect strain rates to stresses. Okay, you know what this is. But basically, what these things allow you to do is it allows you to switch from this viscous behavior, like honey-like behavior, to this behavior where it becomes plastic, where you can shear things, it becomes quite. It changes behavior to some extent. So that's what these things do. It's a very nasty nonlinearity. So these things happen at every point in space. By the way, you have to decide. The equation is to decide, right, in which regime it is in. Is it in the viscous or the plastic regime? And it turns out for these kind of equations, when it's nonlinear, when we're going to solve this with Newton's method, the spacing of contraction of Newton's this is very tiny. So solving this equation is extremely difficult because of that. Okay, so one can do some work and one can actually show that these equations, there is an underlying optimization going on here. These equations are the first order necessary conditions of an energy minimization problem, some viscous nonlinear energy. That's good to know and I use it, but I won't talk too much about it. So there is some optimization problem that leads to these equations. I try to point it out because often I think we solve equations that come from an optimization problem. Because a lot of stuff in the real world comes from energy minimization. Right? A lot of things, elasticity, all these things come from minimization of something. And I think often we tend to forget that it comes from an optimization problem and just try to solve these nonlinear equations. But if you have that additional information, you can often use that to come up with better methods to solve these equations. So that's why I like to point out there's an underlying minimization problem that where you minimize over some energy, overall velocities, over the velocities that are incompressible, divergence free, that's what this means. And it's some convex but non-quadratic kind of complicated energy. So that leads to these two Stokes equations. So that's not too complicated, but so that can be, something can be useful. And then to show you for a very simple problem, how when you apply a Newton's method, how does this do this? How does it behave? Okay, so what is shown here is number of iterations on the x-axis, and the nonlinear residual, the thing you want to make small, want to make 0 for Newton's method on the y-axis. Okay, and let's just look at one color. Let's look at the red color, let's say. And if you try, we try different methods. Then this is actually quite simple problem. It's quite simple geometry. It is not what I eventually want to do. And if you just try to solve this nonlinear equation with what's called Picard method, the fixed point iteration method, it's even simpler than Newton. This is the convergence you get, basically. So after 100 iterations, you haven't made it anywhere. Right? It's not convergent. Too slow. If you do Newton's method, this is the value you get. You basically do a lot of steps, right? Eventually, you get fast convergence. Why is that, right? Because you've searched around here a long time, and eventually you make it there, luckily, right? And then Newton kills it very fast, very nice, right? The problem is that this search for a more complicated problem, this can be extremely long. So it might be that you need 300 steps to actually even get maybe there or not, right? So that's the problem about Newton's method. And with this modification, I'm going to show you quickly, we get a convergence that looks like this. So basically, like in 15 iterations or 12 iterations, you make it, you work with something, it's nice. And actually, I can keep on running this and I can make the residual extremely small. So I can solve this stuff. So that's the kind of that's the improvement we get. And so what are we doing? The same trick I've shown you before. This is just saying it didn't work, but basically what I'm doing is I take these two equations for velocity and pressure. I introduce a new fake variable called, that's actually a tensor, a 2 by or 3 by 3 matrix called tau. And I now write down my Newton step in the original variables, velocity, pressure, and this tau. I've blown up the system. Now I linearize it. So this should feel boring because I've shown it before for this simple problem. Right? So I linearize it in this higher dimensional space. Then I eliminate the extra variable again, the tau. And so I linearize. Okay, sorry, step back. I introduce this new variable. Then I do a nonlinear transformation that's not an affine transformation. So I do a trick that changes the Newton step by multiplying with this g from x at the beginning. Then I linearize, eliminate, and then that's it. And so that's the whole trick. And I'll spare you the details because it's kind of messy to do this. It's nonlinear PDEs. It's kind of, it's many ways to get things wrong. This is what you end up with. This is it in an abstract way, right? So all I do is I take this tau. This is actually easy. That's no problem. I just call the ugly term before. I call it tau, and add this is a new equation. Tau is just this visco-plastic term, right? So here, this is how I introduce my new variable. And now I'm doing the nonlinear transformation. This is where all the action happens. So I take this. This is an equation for every point in space. Okay, so the pointless equation. And I know that this term here shows up here. So this is some massive function. It cannot be 0. So I can always move it to the other side. So this is equivalent to moving it to the other side. It is similar to kind of moving the 1 over x to the other side before. And now I get this equation. I place this with this equation. And then I linearize. I eliminate the fake variable introduced. I get a new Newton system that behaves nicer for the same reasons as before. Here's a comparison of the system, just to point out that they all look messy, so don't worry about details. They're all systems in velocity and pressure, so they're all systems after you discretize them. These are PDEs with discrete space, they become very big. This is when you just do standard Newton, that's messy, right? And if you do after this trick, right, you get a system that looks very similar. There's some modification here in this linearization of viscosity, but that's basically it. In terms of effort to solve this system and this system, there's no difference. Same size, same number of degrees of freedom, same structure, not a big deal. Okay. And we have to be a little bit careful in this modification. You have to be a little careful that we modify this slightly in the sense that we respect the fact that there's an underlying optimization problem. That's why I also want to point out this optimization. If you do this, you get much nicer convergence. So that's what I show you first for a simple problem and then for the real, more interesting problem. So you basically do scientific computing. We approximate these solutions with finite elements. Nothing too fancy here. We do something for this extra fake variable. I show results actually that are computed in Phoenix, if you know what these are. It's an automatic way to kind of compute finite element things. And some of the results, the large-scale results I'm going to show you afterwards, they're implemented in a manual parallel adaptive arbitrary library code that includes many years of work by many students, including some of my work. So there's a simple version, but then we also, because we want to solve really large problems. And everything is iteratively solved. So everything is done with iterative solvers because the problems are interesting are too large. We cannot just use backslash and MATLAB, right? It's way too big. We're going to talk about big systems. This is the benchmark I showed you before. I don't think I need to talk too much about it. There is some symmetry breaking feature here that leads to, it kind of makes these things show up here. So basically this is this sandbox, or this box we contract to both sides. It's a benchmark in this community. This is the convergence I basically showed. I showed you these things before. So you see that if you don't do this trick, right, this is again not the most complicated problem. Right? You might have to take many hundreds of steps or never get there before you get into the huge Newton area. With these tricks, you can always do it like this. And the reason, this is a messy plot, the reason for this is if you're out here with the other method, the steps you can make are tiny. You do a lot of damping. You start somewhere, you can only make tiny steps because it's such a hard problem. With our methods, even out here, you tend to make very large steps and then get very fast conversions. Yeah?
I feel like this fluid situation, is there a physical interpretation of what the nonlinear transformation is doing to the fluid?
But it's solving the same equation, right?
Yeah.
I mean, the fluid equation doesn't change, right? I mean, you would have to interpret to what extent the linearization is different and what this means. But I don't care about the linearization because I still solve the same nonlinear problem, right? So I'm not sure if I can interpret what's going on here. I don't really know. But somehow you see, with Henry argument, you see that the nonlinearity becomes more harmless. You can see somehow that it's easier to solve. Or, I mean, again, it's hard to do this rigorous for these complicated problems, but there's some indication why this works so much. And it works for all kind of different, it's quite robust. That's the whole story of this program. And let me kind of show you that we didn't just do this because it's a nice problem. So these are my last maybe 5 slides or so. So as I said, right, this was not to try to find an application problem. This was a problem I've been working on for a long time. It has to do with, because it's a very nice, very difficult scientific community problem. It has to do with what's called mantle flow. So our Earth, our planet, is made up of 3,000 kilometers of hot rock, high pressure hot rock, okay, that moves, that flows. Okay, it flows the same way that the glacier flows, very slowly, even way slower than the glacier, right? But it moves like a fluid. It's a reasonable assumption to model is a fluid. Inside of the core, I'm just telling you because I didn't know this before because I am sure. So inside it's actually, you have liquid metal inside our Earth, which is the reason why we have a magnetic field, because this moves around. And then the inner core is actually solid metal. Yes, interested? So these 3,000 kilometers, this flow there over millions of years is the reason why the plates are just swimming on top of these things, and they move because of the flow down there. What's driving this flow down there? The heat from the core wants to escape. Okay, so it pumps energy into this thing, and that's why things move, right? Over millions of years. Okay, so this is what drives the plates that float in this thing. This is what drives it, basically. And this is also that's why it's the reason for earthquakes and all this stuff. So that's what we're gonna simulate. And this equation, a very simplified version of this equation to describe this, is a more complicated version of the equation I showed, of this nonlinear equation. More comes to it. There is like there's forcings, there's a bunch of additional things, but one of the core has this. That's the main hardest nonlinearity. We include plates. The plates are not, I'm assuming the plates are also modeled as a fluid. They're modeled as a much more viscous fluid, so as a much colder and that's more viscous fluid. This whole thing is more or less one nasty big nonlinear system of a nonlinear equation. So as I said, I'll skip all the details here, but basically what you need to do is when you use, even though you use, it's a big problem, okay? And you need very fine resolution in some spaces and very large in other spaces. Why do you need fine resolution? In places where one plate gets pushed underneath another one, you have to resolve things on a scale of kilometers, okay? While the globe, the whole thing is huge, right? So you have a lot of sophisticated methods that go in there. There's a handwritten solver that is parallel adaptive. It's based on octree meshes. It's a way to kind of keep track of finite element meshes in parallel. We put in all the geological information that we know. So this is in collaboration with geophysicists at Caltech mostly. But the crucial thing is that this kind of nonlinearology behavior. And so typical runs, typical size we need to even to resolve this kind of system roughly are the order of 500 to 500 millions, 500 to 1,000 billions degrees of freedom. So these are large systems, right? You can't fit that anywhere. And you have to run it, you have to kind of have code that can deal with these things, these solvers and everything. And that runs typically on around 5,000 cores processes, yes.
So is there sensitivity because, I mean, the crust is essentially a solid, so it will be compressible. There will be a Poisson's ratio other than 0.5. And so did you ever investigate the sensitivity of results to things of that nature?
I know there's people, so I mean, there's a whole community does this, and there's some people that do compressible natural convection. No, I mean, it's too messy. I mean, we're just happy to kind of get these things to solve.
And I guess the second follow-on, I mean, you have volcanoes because the rocks melt at the subduction zones.
Yes.
So clearly there is phase transformation there.
But the question is if it really matters. Most of the thing is, it's the energy that's being used as far as I understand it. I'm not a geophysicist, but I'm hanging out with geophysicists for a long time, so I guess I have some understanding. The main restricting force is this very strong plate, and it needs a bend to be pushed underneath it. So I think that's where all the energy dispersion is happening, as far as I understand from these collaborators. So that's the driving part. Yes, there's chemical processes that lead to melting and volcanoes and stuff, but at this level, I think that doesn't seem to be a crucial influence, as far as I understand. Okay, so let me show you how this. So the whole story is we can actually run these simulations, and this is an outcome of this thing. So we've done a simulation of putting forces. Forces means these black things, the blue things here are actually plates. These things are called a slab. So that's a plate that's being shoved underneath another plate. It's all very brutal. This is the core. This is where it becomes liquid metal again. Okay. So you can imagine the dynamics. If you zoom into these regions, you see that there's very fine things that are very important for this overall system, because this plate needs to bend, and where it bends, it needs to change from viscous to plastic, and being slid underneath this other plate. Okay, you see there's a tiny. You need to have quite a bit of resolution to be able to do that. And if you zoom in here, see if that works, right? So this is kind of the computational mesh we use here. So we use these are the cells, right? So we use a quite coarse set of cells here, and the more things we have to resolve, we use quite fine meshes. That's why you end up with a quite large problem. And you can, if you're into units or a physicist, right, you can see that here, you might not be able to see it, but you see the kind of the velocities. So velocity is viscosity. Viscosity is extremely viscous. So we're talking about viscosity from 10 to the 22, then to the 20s. Right? It's very viscous, right? It only flows over billion years time scale. And the kind of cool thing is we kind of put in the forces. We don't force anything for these plates, and then we discover these plate motions on the top here. So these are the arrows. You can see that this is a plate boundary. So there's one plate being shoved underneath this plate. We don't force anything here. This plate is being pulled down there, and it's bending, and it's free to do whatever it wants to. And then we compare these plate motions we get out of the simulations to actually plate motions we observe from satellite. So we have some check, right, if our system that we just put in forces but we let it do whatever it wants to do, right? If that's it compares well with what you observe, right? As a check if we're doing something right here. that all comes out dynamically. This runs, typically, as said, just one solve of this equation is at the order of 10 hours on 5,000 processes. So this is a pretty big problem. And these are comparing the plate motion simulation data with plate motion, with simulations with the observations from satellites to see if we are close. So anyways, we can do these simulations, and there's more to say, but I won't worry too much. And so we used it for this one kind of trick, and that's the story I can explain. So there is reason why we have we know historically what these plates, we know very well what these plates did over the last, how they moved over the last, we can go hundreds of, 100 million years, or we can go quite far back. Okay? So we have, maybe you've seen this, you can see how these things move. There are some reconstruction techniques to help. And there's this mystery, kind of. So the biggest plate is the Pacific plate. It's this monster here, it's the biggest plate. Okay, you see all these other plates, they move against each other, right? And these arrows mean motion per year, and typically it's in the order of 5 to 10 centimeters, right? That's all they move, right? And then, because they move, here's Japan, whatever. So, and so because they move, then at some point they slip rapidly, and that's what causes earthquake tsunamis. Okay? So the mystery is, this Pacific plate, we know from historical data, and I'm sure you can see this, that this thing changed its direction very rapidly, 50 million years ago. Right? Kind of it's a weird thing. You can imagine this is quite heavy and quite, it's not going to change direction easily. It used to move upwards, and then 50 million years ago, it suddenly meaning in this time scale, it means within 1-2 million of years, and suddenly it changed its direction very rapidly. It's not clear why it did that. There's all kind of theories out there, and what we did is actually we can now test some of these theories to see if something that gets suggested is actually able to do that, because changing this direction, you need to have something rapid must have changed. Okay? And it turns out there's been one theory out there that, and there's some evidence in observations, right, in data, that explains it. And the theory is that there used to be, so it moved northwards, and there used to be some, what's driving these things is slabs that are these heavy things that hang down into the mantle, again, everything very slow, that pull it down. Right? And one of the theories that there used to be like, it's called a trench, somewhere up here that pulled the plate northwards, and then at some point it disappeared because it got pulled into another trench, and that force disappeared, and then other forces took over, and that's when it changed the direction. That's a theory, okay? And with these tools, right, we can actually study if that's actually possible, just in terms of forces, right? If we put everything in and that's just not going to make the difference, right? Then we can at least say, that's not very likely, that doesn't explain it. And other theories that have done, we've tried them, and they're just not strong enough to explain this rapid shift. I know I have like 5 more minutes, but I want to show you just really, you see these change of directions in Google Earth, which I kind of find really cool. Okay, so I guess we are here. Let me zoom out a lot. Okay, that's a lot. Okay. Okay, so that's a planet, and the interesting thing is you can turn on this view, right, which actually shows you mountains, but it also shows you bathymetry, so it shows you the depth of the oceans. Okay. And then, as I said, I'm a mathematician, I'm not a geophysicist, but it's very cool to see each of these things. So what happens here is the following. So when you look here at the depth of the ocean, this is Hawaii down there. Okay? And then what's basically happening here is Hawaii is a volcanic island. So there's under the ocean floor, there's like some thin crust that it spits kind of, very nice. I apologize if you're a real geophysicist. It spits kind of lava regularly. So it kind of, you keep track of, and this plate moves, right? So you keep track of where it moves. And you see it here. So these things, these are kind of mountains underneath the ocean floor. Some is there outside, right? And so this tells you that this plate in the last 50 million years just moved in this direction, right? Because this hotspot cone where it spits lava has moved a little bit, I think, but it has mostly been there, right? You can imagine. spits lava every so often, okay? And this plate moves on top of it, above it. Okay, sorry. Challenge here. Spits it and moves above it. So that's how you keep track of where it was, right? And then when you go up there here, so you see that's particle. And then you go here, and look what happened here. So it took a turn, right? Like this is 50 million years ago, right? That means it used to move this direction, and then suddenly it cut a corner here. Okay, so it changed direction completely within a not too long of a time. So that's, you see, kind of, it's kind of, I like that you kind of see these things just in Google Maps, which we use every day, right? So yeah, so that's the thing, that's the mystery, okay? And yeah, and so with this theory, so anyway, so with this ability to actually simulate these systems, right? We have this one theory that there was this one slab here that pulled in this direction, then it disappeared because it was jumped on it. So we can actually study this, and it turns out with this is the only setup we could do, right? That could explain the jump. So here is basically the change in the angle of the motion. This is around 50 million years ago. This is what we can. So these are, okay, some of it is data. So the data, the dotted lines are data, meaning observations. We know it from this volcanic activity, but also from other things that it changed its direction. So it changed around 50 million years from an angle of 30 degrees or minus 30 to 65. And with these simulations, with the theory, we can actually now just run this thing and see if we can explain it with our models. You see, with this orange, this is our simulation. We ran it with the setup of forcing everything here. Okay, 10 hours on 5,000 processors, a lot of code, messy, right? Difficult. And then we ran it with the setup that we estimate like 2 million, 3 million years later, and then we really get this complete shift in direction. So we can explain this phenomenon by doing simulations. And to bring it back to the whole thing, the reason why we can do the simulation is partially because we can resolve this nonlinearity that allows us these plates to bend. Yeah.
So what is your box and whisker plot? Like, do you do UQ? Like, how are you doing this? Like, there's an uncertainty on the deterministic model prediction, or?
There is no uncertainty here. You mean here?
So yeah, what are the?
There are just different setups, different scenarios we ran. There are different scenarios where we use different scenarios with a plume or without a plume. So there's some different, slightly different forcing setups we put there, and there's evidence for those or without. And we try to understand what of these scenarios gives us actually a reasonably sized jump. And we did, here I'm showing you what works, right? We did a bunch of things where we tried other things out, we tried other things that would not explain this rapid change, right? We would maybe go here, right? But it wasn't enough to make this switch complete. Okay, that's it actually. So the whole story that I'll tell you was a little bit that, yeah, so we started very basic, Newton's method, what can change the Newton's step and what cannot. I gave you examples for where these things is done, and I have to admit, right, I've done these things for some time now, and was something similar, right? That's one of the things I do. And only more or less recently, I fully appreciate how close this is to becoming primal-dual, like the 0-point methods. We do this trick, we go to highly measured space, do some modify there, right, and then go back into this. There was something important I wanted to say, which I guess I didn't say. I wanted to say something important, but I didn't recompile. And I want to say, right, I showed you these things for this Western model, but it's not these structures, when you see them, right, that you can play these tricks. This doesn't always work, right? Or use. We just actually today, we finished the paper where we do something similar for a quite different problem. It just has to come with a model of sea ice. So it looks very different, it's much colder, the Earth is a very different regime. Turns out the solvers that people typically use to simulate the motion of frozen water, sea ice in the Arctic, satisfy typically something called hyperlaterology, and it has similar structures, and the solvers they use are really bad, I think, or they are not. Yeah, anyway, so we applied some similar, I did some video, sorry. We applied, because it was similar tricks there, right? And this is used in climate predictions, right? I mean, many codes run these things because you need this component when you model a system of ocean, climate, atmosphere, and stuff. we are using a similar trick in this, again, nested system of equations, and actually it makes a big difference. So it's not, and there's other problems where you can do similar tricks, right? Yeah, and then I try to apply it to show that it enables actually some simulation that tells you something about the plate tectonics, about the Earth history. That's it. Thank you.
So just a curiosity, so for your von Mises viscoplasticity model, is this like a typical von Mises where you're sort of invariant under hydrostatic stress? Or does hydrostatic stress play a role in manifestation of plasticity in your model?
Hydrostatic stress, does it mean you have a depth dependency of the model?
Right, yeah, so.
We have a depth dependency of the model.
So there's, the component of the strain, I didn't ask about it, but you had epsilon dots as a strain rate, and the two lines, was that like second invariant of this?
Yes.
Okay. And so that's like, so then as you go down the hydrostatic pressure, the thing that changes the volume of the differential element would be, that's important in your model then?
Yes, I think
okay.
so. As far as I understand, so basically at every point in the pressure changes when you go deeper, and that changes slightly at what point you switch between these two rheologies. I guess that's what hydrostatic pressure is. I think there's also a rheology where it depends on the dynamic pressure, but this doesn't do it. So yeah, but it changes at a point. You can just I think we have that. I think you need it, otherwise you don't get it right. But there is this Drucker-Prager. There's some formulation that is very messy and nobody knows it has a solution. Whatever. That's not what we use.
Okay.
This is still something messy.
So you explain how your modified Newton's method can be used to better solve these kind of systems. Could you tell us why these shear zones arise in the first place? Is there mathematically to tell us that they're like shocks or something, right? There's something that is spontaneously arises from the
yes, but it's
mathematics.
in a steady state system, right? So they're not really shocks. They're just like basically what this means, right? If the shear rate, if some quantity is above a certain threshold, this material just starts failing. It's like a little bit like yields. It becomes like weak, right? I mean, in a certain regime you push it, right? In a certain regime it's more or less elastically or viscously nice, right? You push it too hard, it's like steel. It's like plasticity in solid mechanics. And it just like then becomes very weak, and that's why you get these shear zones. And you see it from the rheology how it switches. You kind of see it here, right? So basically the effective viscosity, so that's what this kind of is. This is zero, if you get it. So it kind of switches between these two, right? It's the minimum of these two, and if this is the minimum, then you're in this plastic regime because you divide by the secondary of the strain rate, so I didn't explain this. Versus in this regime, it's just linearly viscous because it's just a constant. So this is what does this switch.
And once that starts, then you're relying, I guess, on your adaptive measuring to get resolution where that starts up.
Exactly right, because it's quite thin, and if you don't resolve it, exactly. That also makes it a nice problem when you want to use other things. Exactly.
Is the thing that makes the Newtons hard the separation of scales? Or is it?
I don't think so. I mean, I think the thing is, so roughly, right? So if you have a nonlinearity, it looks like this. So this is, forget this, the yield stress is a constant. Think of it as a constant. Divide by, this is like a gradient, almost a gradient or something. So you have an expression that is just, that looks like gradient divided by the norm of the gradient. That's at every point, right? That's intuitively not a nice nonlinearity to some extent. It's kind of like, so what all we kind of do on a very high level is we multiply this after linearization, this gradient to the other side. So instead of having some gradient times the norm divided by the norm of the gradient, we have the norm of the gradient times something, and then the gradient here. That's a nicer nonlinearity to some extent. It's a hand-wavy argument, but I think that's what the underscore where it's going on.
Is there like a general idea of what a nice nonlinearity is?
So, no, quadratic is nice. No, I don't think, I know that if you try it out, right? The quadratic one is nice, but if you have a product of two variables, that seems to be much nicer. That's what kind of you get there. I don't think it's a general idea. I guess it means that nice means the the derivatives decay quickly, right? Nice means that the second derivative is 0, right? Then it's a linear model. So I guess you can quantify nice by just looking at the derivatives, right? But I'm not sure if there's a general notion. I'm also not sure. Yeah.
So maybe if if I were to build like a mental model, is this like this is kind of like preconditioning or something where it helps to know something about your system and there are some general tricks, but you're not guaranteed to get lucky.
Right. I mean, so it's kind of like I think it's kind of like a nonlinear preconditioning. Even though you have this nonlinear system to solve, right? You kind of modify it, change it, right? In that sense, I think it's kind of a nonlinear preconditioning. Yeah, I think that's kind of what helps you. I mean, that's one way to interpret it. Okay, so I'm not sure. Is that back or you're the boss? Maybe it's good.
I will defer. I guess.
Maybe lots of questions.
I was wondering if you're aware of the mixed variational problems in nonlinear finite elements.
Which problems?
Mixed variational problems.
Mixed variational problems.
In those as well, we have an optimization energy and
Sure.
we come up with the equations, and then
Sure.
we kind of do a variable change and then go back
Sure.
to
Sure.
the original equation with some Lagrange multiplier. Yes, I
Like
think
for Darcy flow.
Sorry?
For Darcy flow or for when you introduce a new variable, but yeah. But
Yeah.
I know this, of course.
Yeah, but I don't think they usually remove the new variable, like what you're doing. They have that extra variable, something like
Exactly.
a Lagrange multiplier.
Exactly. But the motivation there, as far as I understand, is a little bit different, right? Because typically you want to conserve something. When you do it for Darcy flow, you want to conserve the mass flow, and by using an independent variable, you kind of can show that you get this automatically. I think the motivation there is a little bit different. I agree. On formal level, it looks very similar. I agree. But I think the motivation might be different there because you do it even for linear equations, right? You introduce.
I've only seen it for solid mechanics, and I've also seen it being used for plasticity as well. And in general, like personally, I've used it to, like if I have a higher order equation, such as a fourth order
of course.
equation,
Yeah.
then I would want to reduce the order and
Sure.
solve it from
Yeah.
linear.
Sure. So
shape function.
biharmonic, right? You introduce a new variable.
Yeah, kind of like that.
Yeah, to some extent, same trick, but the motivation might be different, right? Because here we're trying to lower the nonlinearity. There it's to achieve certain, I think, as far as I know, achieve certain properties of the gradient of these extra variables. But yes, formally it's very similar. Lexi, you want to?
So there are other ways to fix Newton, right, rather than doing a nonlinear preconditioner, especially when you have an optimization kind of viewpoint. I mean, the simplest one would be a quasi-Newton low memory BFGS method with rule conditions. How does what you're telling us compare against not the tricks, but just standard methods of optimization that fix Newton?
But I mean, I don't think BFGS fixes Newton, right? It just prevents, you don't need to.
Well, it makes it globally convergent.
But it doesn't help you, right? You're still solving the same Newton step system, right? You just have an iterative way, BFGS, to approximate the Jacobian and the flat, that's right. But the nonlinearity is still, I think, the same. It doesn't fix it. I mean, it fixes it the same way as like line search with respect to the nonlinear residual fixes Newton, but it doesn't help you. It doesn't prevent you from taking 5,000 steps to get from here to here. Right? I also don't think BFGS would do that, as far as I understand.
I see. Okay.
Because the equation is the same, just a different approximation to solve, as far as I understand.
Okay. I mean, here you did the change, but you still don't know whether the change was a good change or not. It seems to be you tried.
The way I presented this, by the way, comes out of very, seems it kind of a little bit random here. The truth is, because you have this convex optimization problem, the same way in linear programming you have a dual problem. In general, for a convex optimization problem, and this is a convex optimization problem, you also can describe it eventually also like a dual problem from convex optimization. So there is a dual problem for this, right? And it turns out that the variable for the dual problem is exactly the one I introduce extra variable. So it's not completely arbitrary that I just randomly pick something and replace it. There's some structure to it that plays a role like this works. So it's not just guessing and whatever. I think that's probably not the right thing to do. There's some structure that I kind of didn't explain to you, but there's some to it. Which probably also means that this doesn't always work, right? But it turns out many problems have actually a structure that you can explore. So as I said, there's the CS problem, it's the same thing. I think there's like in mechanics, there's friction problems. They have a similar structure as well. where you can do singularities.
So, given time, maybe we'll take the last couple of questions if there are any offline, and let's thank Georg again.